Hello everyone, we are Group 3. Our topic is about future toilet. We decide to develop a system to make urine usable.
Our project deals with the urine recycling problem. Actually, recycling urine is not a new concept. It was already used in Singapore with the nickname of toilet to tap. However, in normal recycling or treatment process, the urine need to come all the way from toilet to treatment plant. The cost of transportation and treatment is highly demanding and costly. What if we can just immediately purify the urine and make use of it like wash our hands as a supplement of water usage in toilet? We can save the energy and water. In our project, we employ an advanced technique called membrane distillation to purify the urine and then make use of it immediately. It is driven by solar energy. We'll talk about it later. This is a normal wastewater recycling flow. The wastewater first goes to treatment plant to remove the solid particle, then undergo disinfection to remove the bacteria, undergoing a lot of treatment before we can make use of it. Let's have a look at the amount of urine generated. We produce about 0.8 to 2 liter urine per day. If there are 400 people going to toilet per day, the total amount collected would be 560 liters. So let's compare with the water for hand washing. The average time spent for hand washing is 6 seconds. The faucet flow rate is 1.5 gallons per minute. Number of time going to toilet per day is 8 times per person. So the amount of hand washing water needed for a single person per day is about 4.5 liters. If we can utilize the urine generated, the maximum percentage of water supplemented by urine is about 40%. Although the percentage is not too high, in areas where water resources are scarce, if there are large amount of people, the additional water can save a lot. Let's look at the energy consumption. For imported water, the most energy consuming process is supply and conveyance. The interesting thing is that even the energy required for advanced treatment process, like the one in our project of direct potable reuse, is higher than that of imported water. The difference is offset by supply and conveyance, which make direct potable reuse an energy effective process than imported water.
Thank you, Jerry. For some existing technologies that are similar to our project, first, I will introduce recycling astronaut urine for energy and drinking water by using the urea bioreactor electrochemical system. For its mechanism, the urine and the shower wastewater are processed using forward osmosis, which is a way to filter contaminants from urea. Actually, the urea is efficiently converted into ammonia in a urea bioreactor. And then the electrochemical cell converts the ammonia to power. Through the UBE systems, more than 80% of organic carbons are removed, and 86% of the urea are converted to ammonia. Therefore, it can be applied in contaminant recovery from wastewater to useful resources and energy. However, the urea tends to be poorly rejected by forward osmosis membranes, and then is accumulated in osmotic agent loop to contaminate the water. Hence, it cannot be used in treatment for drinkable water. In addition to UBE system, I also want to introduce a portable device called Aqua H2O. It is useful to turn pee into drinkable water. Let's look at the structure of this device first. As you can see, it is mainly comprised of activated carbon, microfilter, and osmotic membrane, which are used to filter out unused substance in urine. How to use it? First, users should urinate on the activated carbon to eliminate the color and the flavor of the urine. Then, make pressure with needles to filter the urine through the microfilter and 1000 micron osmotic membrane, which can filter virus and bacteria. Finally, the drinkable water can be passed by pressing on the cylinders. Users can drink directly through spilling spout or keep in other container. This is a portable device for water shortage areas. But whether people are willing to drink the water from their urine is the main concern of this device. Those are the similar technologies to ours. Next, I will pass the time to Anson to talk more about our technology, which called air gap membrane distillation in detail.
In our process design, the equipment setup is quite simple. Once we connect urine from toilet in a storage tank, urine is then pumped into the water purification unit. During the pumping process, pressure and volumetric flow rate are increased in order to establish a desired inlet state for purification. After the purification unit, water and impurities are separated. Particularly, the pump used in the process could be operated under the solar cell energy supply. The reason is the solar membrane distillation does not require high flow rate and high pressure for purification. So how can we purify the urine only by solar energy? The detailed structure looks like this. We integrate the solar heat exchanger with air gap membrane distillation technology to perform a low energy consumption purification. The key purification process is driven by the temperature difference of hot urine and cold urine. These two streams are in counterflow direction, and they were divided by an air gap. The temperature difference increased the vapor pressure, leading the water molecules evaporate through the membrane and condensing at the condensing plate. This condensed permeate water is then collected in a storage tank for further application. The eluate impurity will be disposed as waste. That's the overall mechanism of solar membrane distillation. Here are some detailed design allowing urine membrane distillation. It can be operated at around 60 degrees Celsius under low hydrostatic pressure. Therefore, it benefits from the energy cost. What's admiring is that membrane distillation is not resisted by membrane fouling due to its mechanism. According to certain studies, at least 75% of available water is recovered in water treatment by membrane distillation. Lastly, the material of the condensing plate has to be high thermal conductivity to enhance the heat exchange for condensation. You may ask, what is the difference between reverse osmosis and membrane distillation? The energy density of reverse osmosis is relatively greater than membrane distillation, about 3 times. Also, the water recovery of reverse osmosis is relatively lower than membrane distillation in around 2 times. That's why we chose membrane distillation technology for urine purification.
Thank you, Emerson. Refer to the graph, which shows the potential of membrane distillation in seawater desalination. In our project, the results are optimization because we use urine instead of seawater. Considering heating and membrane cost without water cost, the minimum cost was $0.5 per meter cubic, obtained when operating at a temperature gradient of 45 Celsius degrees. Let's look at the pros, the potential advantage of membrane distillation in comparison with conventional separation process are found primarily in the lower working temperature and pressure, and thus the lower energy cost and less stringent mechanical properties. In contrast to distillation and reverse osmosis, supply solution can be separated at a temperature well below the boiling point and under atmospheric pressure. Typically, supply temperatures around 30 to 60 Celsius degree permit reuse of residual heat flows and the use of solar energy. In addition, in comparison with reverse osmosis, membrane distillation is less susceptible to flux limitation caused by concentration polarization, whereby a higher concentration of matter is obtained on the supply side. Therefore, membrane distillation offers 10% retention for non-volatile dissolved substance, whereby there is no limit on the supply concentration. In comparison with traditional distillation, membrane distillation possesses typically basic advantage of membrane separation, namely simple upscaling, simple operations, possibility for high membrane surface per volume ratio. How about the quality of output water? Actually, it's quite high. The radius of virus is about 20 to 300 nanometers, but the radius of space between membranes is 0.001 micrometer only. Hence, it can prohibit virus pass through the membrane.
Composition of urine. Urine is mostly composed of water, which takes up to 95% of its weight, followed by 0.05% of ammonia, and this is the substance that is responsible for the smell of urine. And then 0.18% of sulfate, 0.12% of phosphate, and 0.6% of chloride, and etc. Apart from these, there are also components such as dissolved ion, inorganic and organic compounds. Even though membrane distillation process seems to be sophisticated technology with no drawbacks, however, there are also some technological shortage that we need to overcome. So there are three main disadvantages that we are facing right now, which are membrane pore size, membrane falling, and membrane wetting. Another problem associated with membrane distillation is membrane falling. It refers to the accumulation of material at the surface or in the pore of a membrane due to the deposition of suspended or dissolved substance. This causes the loss of membrane performance because falling decreases the permeability of the membrane, which leads to severe inefficiency of membrane process. It also causes improper purification of water. In this case, urea and other dissolved ion, inorganic and organic compound will gradually pile up on the surface of membrane or within the pore, so it will disrupt efficiency of osmosis. Okay. Finally, membrane wetting also causes huge problem. Membrane wetting by absorbent leads to an increase in mass transfer resistance and a deterioration of absorbing water. In another word, this decreases the efficiency of membrane distillation. To overcome the membrane wetting, the membrane distillation processes must be done under highly aqueous and sufficiently dilute condition. This means that we need to put extra water input in order to make urine more dilute to prevent wetting. However, due to the decrease of concentration, the efficiency of osmosis will decrease with time. So that's all for our presentation. Thank you.